Okay, so we begin as soon as let us let the students begin joining. So, uh, very good afternoon once again, and welcome you to this online live interactions on the course offered on the NPTEL SWAM portal, which is on Mass Transfer Operations. So, we have went through the 4 weeks: week 0 dry run, week 1, week 2, week 3, and week 4. And today we are in the week 5 of this course. So we have seen some of the basic fundamental concepts during this week until the week 4. So from the week 5, it's like some of the modeling concepts as well as some of the things that are used in the operations related to the mass transfer. So what we are going to study is that some of the basic operations which have been predominantly used in the chemical industries as well as some other industries, pharmaceuticals, and so many industries have been using these concepts. So these concepts include the operations which involves mass transfer as well as heat transfer, but we will mainly focus on the mass transfers and the operations involved in that, like gas liquid operations, liquid liquid extractions, distillation column, and so many to go. So again, just a quick one. This course is on Mass Transfer Operations 1, which is a basic course for undergraduate students in chemical engineering. And this course has been offered on the NPTEL SWAM portal by Professor Vishnu Pandamandal, who is a professor in Department of Chemical Engineering at IIT Guwahati. And myself, I am teaching assistants. I will be teaching assistants for this course during the entire tenure of this online live interactions, that is from July to October. And myself, Rajpush Shubhamanji Kumar, I am a PMR scholar in the Department of Chemical Engineering at IIT Madras. So, like I said, I will be taking your online interactions every weekend, that is on Saturday, 3 to 4 p.m. Okay, so this is the week 5th actually, and we have already gone through all the week 4 courses, and along with that we have gone to the lecture notes for that also, and we have solved some of the numerical problems related to the fundamental concepts. Plus we have seen what is the various laws of mass transfer, like fixed first law of diffusion, fixed second law of diffusion, and we also gone to the some anonymous related to the mass transfer, and some dimensionless numbers in mass transfer, like Reynolds number, Prandtl number, Sherwood, Stanton, Packlet number, and we also solved some of the problems related to that. So from the week 5, as mentioned on the NPTEL online portal, the course is this course from now onwards will switch to the operations technologies, that is related to the gas liquid operations as well as to the mass transfer operations, which involve some of the instrumentation techniques which has been used in the chemical industries as well as in the refineries also. So this includes like the distillation column, gas liquid operations, which includes absorption columns, pack back towers, and so many fundamental concepts related to that, how you can design these columns for a particular output. So suppose if some industry is there, like a refinery or a petrochemical industry, and they want the particular product from in order to separate from the mixture or an isotopic mixture, so they want to design a distillation column. So how you need to design a distillation column? So every concept we are going to learn in this for the remaining tenure of the course, that is the designing and the concepts related to the distillation column, gas liquid separations, liquid liquid extractions, solid liquid extractions, and similarly like that. So from now onwards, it's basically core fundamental related to the industries. So it's very much helpful to the guys who are planning to go to the industries after the undergrad studies. Prior to that, it's also might be helpful for the simulation guys, because for the simulation also you need to learn what are the basics of these operations that involves mass transfer in that. So week 5, as per the content on the NPTEL portal, the first involves the introduction and the classification of sparge and agitated vessels. So in this one also, there are different ones, like rotors inside the reactors. Suppose if I say this is a reactor and this is the furnace, or the baffles are there. So there are different types of baffles, or the agitators, or the rotor blades. So you can see these are the baffles, these are the rotor blades, and the different types of the blades, like agitator blade, a rotor blade, and then anchor blades, and how they have been used in order to design the agitated as well as sparge vessels, and so many things are there. But as soon as we proceed through the course, we will be able to know each and everything one by one. The another thing which we have been discussing during this week is the gas disposal, is the tray tower. So this is one of the most favorite topics in the mass transfer, related to the tray tower and the design of the tray tower, and the various different types of tray used in the tray tower. So one is a sieve tray, another is wall tray, and the third one is a bubble cap tray. So this three are the most different types of trays that has been used in the tray towers, but which one you have to implement in order to get the optimal output from the for the product from the resources they've been putting into the towers. So that decides depend upon the quality and the quantity of the you want to process, and also upon the type of the material that you are processing. So these three are the type of the trays which are going to predominantly used. But right now there are also different drawbacks of these trays. As soon as you proceed to the lectures, you'll be able to know what are the facts and unknowns. And the fourth one, last one is the liquid disperse, that is venturi scrubber, wettable column, and the pack tower. So, like the tray tower, pack tower is another one form of like tower that has been used in the chemical industries, particularly for the gas absorptions or the gas liquid absorption columns. So, in the pack absorption tower, you can consider different type of packings like rashing rings, bell rings, ball rings, different type of packings like standard packing, cubic packing, and various packings are there. So, but which packings you have to implement for getting the optimal output similar to the tray towers. So it depends upon the products that you are processing, and also there are some detrimental uh, functions that you have to take care, like there should be no like build up of the water in the sense of the solvent in the column where you're processing the feed. Along with that, there should be no flooding. So these are the various terms which will come as we go through the lecture notes and similar. So this in this lecture, in this live interaction, so this entire week 5 was on the basic concepts of this operation. So we will not be able to solve some of the numericals, but we will be able to go through some of the concepts which has been discussed during the week 5 that might that will be helpful, not mine, that will be helpful for you all of you guys in the upcoming remaining tenure of the course. So like I said, please go through the lecture notes once, because these questions will be directly asked in the MCQs in the examinations as well as in the gate examinations. They will ask the same things. So it carries one quick marks, but unless and until you know the fundamental concepts of that. So we'll start with the some of the basic fundamental, like the gas liquid equipments. So this gas liquid equipment, you can say it is in continuous mode and batch mode also. Second is batch mode. So the continuous mode of gas liquid equipment has many applications in terms of refineries, petrochemical industries, as well as in semi batch industries. So it has many applications. Whereas the case of batch mode, it has fewer applications. That is particularly related to the output of the product. So if you want some specific product with a specific purity, you can use the batch mode in the gas liquid operations. So how to increase the contact between the gas and the liquid, that depends upon a term which is known as the interfacial contact area. So this term you will see between gas and liquid. Okay, and the mass transfer coefficients. Yeah, the another term will be the mass transfer coefficients. So the increasing rate of mass transfer. So how to increase the rate of mass transfer? So these two terms that you have to take care while designing a gas liquid equipment, that is the interfacial area of contact between the gas and the liquid, and the second one is the mass transfer coefficients, which is in order to increase the rate of mass transfer, like I said. Okay. Now, so there are different types of gas liquid equipments, like gas disperse. Either the gas will be dispersed into the liquid or liquid will be dispersed into the gas. So the first one is, I'll change the color here. So gas disperse. So the gas is dispersed into the liquid. Like I said, there are two different things you can do with while designing. So it depends upon the type of the product you want and the process feed you are processing. Gas is dispersed in the liquid, and second one is liquid dispersed. So in the liquid disperse, what will happen? Liquid is dispersed in gas, or it is dispersed in the form of the droplets. In a continuous flow of gas. Okay, so these are two different gas discharge systems that we have seen, and similarly the designing has to be taken care. Apart from this, like I said, there are agitated columns, like the gas will be dispersed or what. So if you just go through the ideal design of the gas dispersed columns, this might be the baffles, if you can see, and you can see there is a motor up here, and there will be a plunger, and this will be the rotor. So this is the agitator, and similarly you can take this as an outlet. So you can take this as vent, this is as gas out, this is liquid out. You can take this as, so we have taken this as a counter current flow of the gas actually. Okay now, so this is impeller. So there are different types of impellers like rotor, blades, and what you can do, you can just purge it. So this is the gas purging, or spurge, or you can say that. Okay, and these are the baffles in order to remove the vortex formation in the liquid. This is the shaft for rotating the impeller, and you can say this is, there will be a manhole inside. So this is some like a basic type of the agitated vessel which you can see. Okay, so these are some of the major different parts. Now the type of impellers, if you can see, there are different types of impellers that have been used in the agitated vessels. So this might, these things you have to remember. Type of impellers in agitated vessels. So the first one will be turbine. The section is paddle type, and the third is disc type. So these are the different types. Oh, sorry. Okay, so these are the different types of the impeller that have been used in the agitated vessels, and along with that there will be baffles to prevent formation of vortex, and manholes in order to clean the during the maintenance times. Like I said, you can place that one also. So these are the different forms and the various things that can be used in the like the vessels and the impeller. Apart from this, there are various different terms which you might have gone through. Oh, sorry. So, like this, there are different types of impellers also, like anchor impellers. And if you go to the lecture notes, then might be given the concepts for the same. So, like I said, so like I said, there will be an anchor, this type, type, turbine shape, disc, paddle. So all these impellers will have the different geometry and on the basis of the type of the process you are doing or you're going to handle in the distillation column or in the agitated vessel, not in the distillation column, in the agitated vessels or gas liquid equipment, you can use the different types of the like impellers based on the process you are going to do, or based particularly determining the type of the products you're going to handle. So this is what I mentioned is particularly related to the gas liquid equipments, or you can say it as the sparge vessels or the agitated vessels only, not for the distillation columns. For distillation columns, we are coming just now to the topic right now. So if you go through the lecture notes, we have gone through some of the concepts related to the tray towers and the type of the tray towers, and along with that, you've also seen some of the uh, what you can say different trays like seed tray, bubble cap tray, wall tray. So like here you can see, so this is one sort of the plate or tray or plate column like I mentioned. So this is tray or plate column. So why it is called tray or a plate column? Because if you go through this, you can see there is a gas purging from the downwards, gas coming in and gas coming out from here. You can see this one gas, and here from here the gas is in. And similarly, you can see that it is in the counter current mode. So first you can see in tray towers, you can see counter current operation. That is gas and liquid flows in opposite directions over the trays and our plates. Okay, so there are different types of the inlets. So for the gas inlet will be there, so gas will be going up and liquid will be flowing from top to the bottom, and you can see there are different type of the trays. So this is the downcomer, you can see. Yeah, so I can just mention it, and I can see the downcomer here. So this is downcomer, this is the tray on which the gas is bubbling up. This tray can be type of the bubble cap tray, valve tray, or the seed tray also. But that's what I said is depends on the type of the operations you're going to handle. So similarly, there are different types of the attachments in this tray tower. So a tray tower primarily consists of a vertical cylindrical shell or a cell of a tower. So it's vertically a cylindrical tower in which there are different trays, like different stages of trays, and these trays, number of trays will also be specific related to the type of the operations we are going to do. So the trays are the plates on which the gas liquid contacts occurs. So trays, gas liquid contact occurs, and the arrangement for the flow of liquid from the top to the bottom is through the downcomer. So there is another term called downcomers. So the liquid flows from one tray to another tray. Suppose this is one tray and this is another tray. So liquid from one tray to another tray through the downcomer. Similarly here the liquid flow is, so this is downcomer. Okay, and the inlet and outlet nozzles are for the two different phases, that is for the gas and the liquid, and similarly it is like the different concepts. Okay, so this is the basic of the tray tower. Like there will be a downcomer, there will be viewers, there will be trays which will be either sieve tray, valve tray, bubble cap tray, depending on the type of products you want to process, and there will be two outlets for the two different phases, that is the gas and the liquid you are going to process. Okay, and so now we will come to the trays actually. So the first one is a bubble cap tray. So sorry, yeah. to the bubble cap tray. So before going to the trays, the major functions of the tray are, so in order to avoid the confusion, trays are also called as trays. Okay, so the major function of the tray, like I said, it has to allow to make a contact between the gas and the liquid, and it should hold some amount of the liquid so the gas can bubble it through that. So that there should be a dispersion of gas from the liquid. So the first one is gas bubbles through the liquid to form a gas liquid dispersion, and the second one is three holds the dispersion in it. So this is what it called as a main function, and a mass transfer occurs. So the main thing is they will hold the dispersion and they will allow the mass transfer to occur. Mass transfer to occur between gas liquid. Yeah. Okay. So the bubble cap tray, like I said, is a bell-shaped tray. I will just, so this is what the related to the trays actually. Change the color. So So the bubble cap tray, like has been shown here, is like a form of a bubble. So if the gas bubbles through the liquid, it passes through the tray, which holds the dispersion in order to make the mass transfer contact between the gas and the liquid. So when the gas goes up in the countercurrent mode and the liquid flows down, so the gas will go through the bubble cap tray, which in the form of a bubble pops up, so and it will give an area to move the gas forward up. So it is a type of a bell shape, like you can see this one. So this is like bubble. So it's a bell shaped cap and in form of a riser slash chimney. Okay, so this is what we call as a bubble cap tree. So in fact, the vapor pressure, no, so different type of tray caps have a different type of the vapor pressure to hold up. So which will be sufficient, which will not be sufficient but necessary for the process to carry out. So it depends upon the type of the process. Like I said, there are different types of trays. It doesn't matter whether it's bubble cap, wall, or sip tray. The only thing is that it depends upon the processes you are going to handle. Whether it's some of the viscous liquid, the vapor pressure between the gas and the liquid will be very high, so that it will try to relate to the flooding of the column. So in the basis of that, so I'm just mentioning the overview, what are the ball caps and how the types are. The another one is the sieve tray. So this is the simplest type of the tray. As you can see, this is a sieve tray, which has been mentioned in the column. So it is the simplest type of tray in which the bubble caps are replaced by the holes. Okay. So this is what is a sieve tray. So there will be sieve perforations, or you can say holes or perforations for the entrance of the liquid. Entrance of the entrance of the gas into the liquid. Okay, so this is what is the sieve trace, and this is so there are the holes are relatively small diameter in the compared to the sieve in compared to the wall bubble cap trace. So this one they are called as small slits, and they are also called as a perforated trace. So sieve tray is also known as perforated tray because there are small perforations, and the holes are usually of the size 1/8 to half inch because they are relatively very small compared to the bubble cap trays. Okay, the another one is a wall tray. So, so this shows the figures of the wall tray actually. And the form of a ball will be sitting from the top. As soon as the only criteria for the ball tray to use is depends upon the gas pressure. So the gas pressure is sufficient enough, the valve will open up and will try. If you can see here that the suppose this is the cap and the gas is flowing to here. So if the normal pressure is that this cap will not open up. So if the gas vapor pressure is sufficient enough, suppose you can see the third one, this will pop up upside and the gas will flow from here, like what has been mentioned in the third. So it's required depends upon the pressure of the gas to carry out. Okay. So this is one of the newest class of the trace that has been developed. So it is relatively new class of tree that provides variable area. So this area depends upon the type of the gas pressure that is going to up, and that's because it's known as a variable area. Variable area for the gas or the vapor. So this is why it is called as a valve tray, and a valve tray is also known as a proprietary tray. So there are different names. So proprietary in the sense it depends upon the type of the pressure. So you can build the valve trays by your own more specifications, but it depends upon the type of the gas flow or the vapor flow bubbling through the liquid over the trays. So this is the another form of the tray. Now the another thing which we have already gone through the lecture notes is the downcomer and wears. So the downcomer and wears. So like I said in the distillation column, if the liquid is flowing from the one end to the one tray to another tray, it has to come through a downcomers and wears. So downcomer makes a contact from the allows the liquid to flow from the one tray to the another tray or from the one tray above to another tray below. So it can be considered as a passage through which the liquid flows from one tray to another tray, or liquid flows down from one tray to another. Okay, and the desired depth of the gas liquid contact is maintained with the help of the weir. So weir is another term here. I'll take different colors. So this is downcomer and this is weir. So and desired depth of the gas liquid is maintained on the tray using the weir. Okay, and this weir is in the form of a vertical plates between the while coming from the downcomer, the liquid flow from the weirs and will flow down to another downcomer plate. So weir is in the form of, and there are different type of like weirs also, like I've shown in this figure actually. So this is, I'm not going to explain each and everything in fundamentals, just we are going to the basic concepts. What are different things that we use in the that are going to be used in the packed hours, state hours, or the distillation columns, so that by solving the numericals, it will be easy to identify the terms that you're going to take out. And like the nozzles usually, like the gas inlet nozzle, gas outlet nozzle, and many more things. So for contacting, so this is known as a nozzles. So a tower for contacting liquid and a vapor or a gas. So we are always dealing with these two different phases, impact tower, tray tower, or the distillation columns should be provided with a few nozzles for. So first one is the, I'll change the color here. So first one is for the feed entry, both gas and liquid. Second one is reflux or reflux to top and boiler, boiler return. And third is product withdrawal from the tower. So these are the very different things that are going to be used, and they will be used in the you can say as the towers or the trays or the pack columns, as well as in the distillation columns we have been provided with the different nozzles and the downcomers and the weirs. The only thing is that we are not going to the numerical concepts as now. We are just going to the basic concepts of what these terms are basically meant and how they really look like. So while in terms of designing it comes later on in the next lectures, it's better to go in an idea with an idea like, oh, these are the nozzles, so they must be used for the feedstock entry, as well as the products exiting from the columns, as well as for providing a reflex to the top of the condenser and from the reboiler to the back to the column to generate the vapor. So these are the very different aspects. So now the thing is comes now the various operational features of the trade column. So these are the three different terms here we mentioned, that is sweeping and dumping, entrainment and flooding. So all these terms have their own fundamental meanings. So if you can say weeping, so like I said, if I draw something, weeping means crying actually. If you can say just in the simple concept, if you start weeping, means if you start crying, the tears will flow from your eyes. Okay, so if the gas pressure, so if you say these are the openings, okay, and this is the gas that is flowing, and this is the liquid is on the top of that. So if the if gas vapor pressure is very less as compared to the liquid on the top of the tray of the column, the liquid will tries to perforate through this. Okay, so liquid tries to weep down. So this is concept is known as a weeping. Okay, so very small fraction of liquid flow from a tray to the lower tray to the perforations of the opening. Okay, so this is known as weeping. On the other hand, dumping is an extreme case of leakage through the deck if the vapor velocity is too low. So, so these two terms have been interrelated. So weeping is where slowly the liquid will flow down to the perforations of the openings from the one tray to the another tray. Whereas in the case of the dumping, entirely like the liquid has been dumped from one tray to another. So dumping in the sense means if the gas vapor pressure is very low, like I said here, the gas or the vapor velocity is relatively low, pressure drop across the tray is not sufficient to hold the liquid. Okay, so what happened, the liquid will entirely dump from the one tray to another and the column will be flooded to the things. And the other thing is entrainment. So entrainment means entering. Entering in the sense if you consider some of the gas flow has been happening from the bottom to the top and the liquid particles have been coming from the top to bottom. But in order to get the enriched product, so you have to have a countercurrent operations also. So if the gas flow is very high, it will enter some of the liquid droplets and carry it forward to the condenser in the distillation column or the tray column you can say. So what will happen in case of getting the like the efficiency at the bottom of the reboiler, because some of the liquid droplets have been carried over by the gas particles because of the high gas velocity. So what will happen? This is known as the gas particles are entering some of the liquid droplets and are taking it over toward the top of the column to the condenser. So this will reduce the efficiency, and this is known as the entrainment policy. And the third one is the flooding actually. So if you can see flooding, so there are different variant terms of the floodings also. The flooding the columns happen if the gas pressure is very high, or the spray internal flooding. Oh, sorry, it's just one minute. Yeah, so flooding. Yeah, we have seen these two terms right now, that is dumping and weeping, and we see the entrainment. So flooding, if you can consider this the last term, so this there are 4 to 5 different terms which have come you have gone across, and this will be directly asked in some of the like questions for 1 mark or 2 mark in the examinations also. So it's better to know what this term specifically means in the column. So flooding on a tree column may occur because of one or more other reasons. It's not like just there is one reason for the flooding. So if you can consider the accumulation of the liquid on a tray continues and it tries to build up and the gas pressure is not sufficient, so what will happen? All the trays will be flooded up to the column. So this is called one of the reason of the flooding. So flooding is an abnormal condition of an excess accumulation of liquid or simultaneous excessive pressure drop across the flooded tree. So what will happen if I can say I'll just light it up right near here. Excessive buildup of the liquids on a tray. Or pressure buildup, which results in pressure buildup. So, if there is sufficient, like more amount of the liquid that has been built up upon the tray, and because of this, the pressure buildup will be more, so the gas will not be able to pass through the perforations or the various caps like sea tray, water tray, bottle cap tray from one tray to the above another tray. So what will happen? This trays will hold too much amount of the liquid on the top of that, and what will happen? The liquid will overflow from the one downcomer to another, and all the trays will be flooded from the because of these reasons, or maybe due to the pressure buildup cases on the tray. So this is the phenomenon which is known as the flooding. Okay, so like I said, these are different terms you need to take care of. This will be coming in the later courses, later time also. But it's better to learn from the state now, from now onwards, because in the questions they will directly add the column is been flooded and it's the liquid rate is this. So you must know what is flooding, what is sweeping, dumping, and entrainment. So just go through the lecture notes, try to see what have been explained, and also see some of the examples. So there are various examples in the industries also. I've also worked in the industries and I've seen flooding in many of the distillation columns, tray columns as well as in the pack columns. So it basically happens because of the pressure buildup on the trays or the liquid buildup on the trays, which are allowed to flood the entire columns, which will stop the entire distillation columns of the operations of the industry, and it's very detrimental to the operations because cleaning a distillation column or maintenance of the distillation column in continuous industries like for refineries is very critical, because once you shut down the entire plant, the cleaning of the because of the distillation column, it will take a minimum of like 4 to 5 months to start it up again. So while operating this distillation column, tray column or pack column, it's very uh, in a very precise manner. We have to do some calculations, modeling and simulations, as well as theoretical designing of these columns, so that prior to the startup of the operations of the columns, we will know that okay, this is the upper limit of the high limit or the upper limit of the things that will cause the column to be flooded, or there will be entrainment in the process. So these are some of the different terms that have been used in the industries as well as in the while designing the columns also. So please go through this lecture notes again and let's see what we can be using these terms in the later point of time. And this is one sort of the performance diagram for the tray columns. So the performance diagram of a particular tray depends upon the relative liquid or the liquid. So I'm writing up what is this performance diagram. And it is also known as tray stability diagram. Okay, so these are the different terms. I'm not going to explain because it will is showing the same thing like flooding, dumping, entrainment. You can see this is entrainment, flooding, heavy weeping, moderate weeping, weep point dumping, and like entrainment. So the terms which I've seen is been explained in terms of a chart, and it's known as a tree stability diagram or the performance diagram of the column. So just go through lecture notes and see what you can get grasp from this performance diagram also. And the last thing is the turn down ratio. So column design for a particular, like you can see like we see it for different column designs, there will be a turn down ratio. So So in order to, because every column or a tray column, pack tower or a distillation column, they have to be designed for some specific purpose, for the specific process to be carried out. So there should be some flexibility in the terms of like trays. So it is therefore desirable that these trays have some degree of flexibility to operate over a wide range of throughputs and the design capacity. So because of that, we need a turn down ratio for that thing. So such flexibility is offered in the terms of uh, I will return flexibility to operate over a range of throughput around the design capacity. Okay, so this flexibility is explained in terms of the turn down ratio, and they have like seen like different types of trays. So the seed tray, wall tray, and the bubble cap trays have a turn-down ratio of about 2, 4, and still larger turn-down ratio. So it's better preferable to go for like seed trays or the wall trays, which are also known as proprietary trays, because bubble cap trays there will be pressure buildup and will lead to the various detrimental conditions which are already seen like flooding, entrainment, weeping, dumping, etc. Okay, and the another point is the tray efficiency. Okay, so the last point which you're going to cover is the tray efficiency. Is that there are different types of the tray efficiency: point efficiency, Murphy efficiencies, and also overall efficiency. So the first point I have mentioned here is on based on the tray point efficiency. The point efficiency is defined as the actual enrichment of the gas divided by the maximum enrichment. That is one particular related to the point. At one point, we're measuring the efficiency. Whereas for the Murphy efficiency, you can say the concentration of the liquid leaving the net tray divided by the equilibrium concentration corresponding to the liquid. So so they have the different formulas which I've already mentioned here. For point efficiency is given by E of OG, and E of mg is the Murphy point efficiency. And one thing is that it is known as the overall efficiencies of the column, which is the number of the idle trays to the number of real trays. So idle tray is that which will be ideally will be there like for the ideal reactors in CRT. That's what I'm going to talk about. But ideally there should be some number of trays. Like I said, this is an idle column and it uses this idle number of trays. Like suppose 5 is the idle number of trays which uses this idle reactor will use. Whereas another is the real reactors, which in the real world problem in the real industries there will be a real number of trays. Suppose it's 100, so its overall efficiency will be 5 by 100. That's depend upon the overall efficiency. So it says the overall efficiency. So the main thing we are going to focus is on the overall efficiency as well as the point efficiency. But in some of the questions, they will also give you a Murphy point efficiency and will let you know to calculate the overall efficiency from the same. So all these three formulas are important and you must have to go through all the things. Once again, if you're not gone, please go to the lecture notes again and again and try to see what are the various assumptions they have mentioned. So for today, like I said, there will no further numericals. Only just will go through some of the MCQs what I've already seen through the lecture notes today. So what is a specific area in a pack column? So what is the specific area in the pack column? Like I said, like we gone through the tray column, a plate column, or a pack column. So there are four different options. So the actual surface area of packing per unit bed volume, total wetted area, effective area of contact between gas and a liquid per unit volume, and the none of the above. So I've been asking again specific area. So if you go on through the notes, you will see for the effective contact between gas and the liquid, you will require a specific area, and the specific area depends upon the effective contact between the gas and the liquid per unit bed of the volume. So directly, if you're gone, if you know the concepts, this is a straightforward questions, and the correct answer will be C. That is the effective area of contact between the gas and the liquid per unit volume of the bed. Okay. So the correct answer is C, effective area. Okay. Similarly, this is one of the MCQs that I would like you guys to know go through. So the grid packing is suitable for gas absorption if grid packing. There are different types of packing, like I said, in the absorption columns. So this is one side of the question. The grid packing is suitable for gas absorption if a large liquid rate has to be handled at low pressure. The feed gas has a high solute content. A large gas head has to be handled at low pressure, and a small gas head has to be handled at high pressure. So uh, like I said, there are different type of packings, and each and every packing have their own fundamental applications to be used in the gas absorption columns. Similarly, grid packings. Uh, uh, since the time is not much more, what I will do is in the next week we'll go through the type of packings also, what different types of packings in the pack tower or the gas absorption columns will be using. So, particularly for the grid packing, there is a concept related to the controlling the large gas rate. So, it's suitable for large gas rate to be handled at a low pressure. I'm just mentioning here directly to the MCQ because we have not covered these concepts in the previous like 50 minutes of lecture. So I'm going to trying to explain through the MCQs. So we are not going to through because this is like a new part of the mass transfer operations we are going to carry forward. So I don't want you guys to directly jump on the numericals. Instead of that, you can go through some of the basic concepts. What is there in the mass transfer operations related to the gas liquid operations, columns, tray, pack tower, different terms related to that, so that in the next lectures we will be able to identify, yeah, these concepts that we already learned in the previous lectures. So we can start on the numericals right now straight away. This is another question. Static liquid hold up. Like I said, in a tray tower or a pack tower or a distillation column, there is a liquid hold up. And if it's a static, so what is the static liquid hold up? So it is the amount of liquid remaining in a unit volume of the bed after the bed is drained for the reasonable time. Drain means the liquid has been removed out from the column and it has been remaining. So what is mentioned is after the bed is drained for a reasonable time. Okay. And also the second option is also called the operating hold up, or the difference between the total hold up and a dynamic hold up, or the none of the above. So the static hold up is, if you can see, hold up of the liquid in the sense the tray has more amount of liquid on the top of that. So if you drain the entire column, what will happen? The amount of the liquid that has been holded up on the tray, even after draining the entire column, it is known as static hold up. So it is the per unit volume of the pad. So the correct answer you can see directly is the A. That is the amount of liquid remaining in the unit volume of the pad after the pad is drained over for a reasonable period of time. So this thing I have already shown through the previous terms like flooding, weeping, dumping, etc. So this is similar to the same concept we are applying here. Yeah, so this is I have already explained downcomer on a weir. The downcomer weir is a bottle to a tray which provisional of the adjustment of weir height, welded to the tray to get sufficient strength, riveted to the tray to protect against vibration, and knuckle to the tray to get strength. So I can clearly mention it's not there to protect the vibration or for the knuckle to the tray to get the strength. The only thing is that the weir isn't provided in order to allow the liquid to flow from the one end to the another end. So it covers adjusts the height of the liquid. So the bottle it's so Downcomer allows the liquid to flow from the one part of the tray, like from the above tray to the below tray. And weir has a vertical plate which allows the liquid flow from above to the bottom of the downcomer to the second downcomer. So it's bottled to the tray. So the correct answer is A actually. Bottled to the tray with provision for the adjustment of the weir height. So this weir height can be adjusted and depends upon the type of the operations you are going to carry forward. So it's like a vertical plate. So this weir is a vertical plate. Okay, and it's in the form of like this, and this will be another tray, and there will be another weir here. So the liquid will flow from here to here, and the here to another tray. So there will be another tray here similarly. So this is weir and downcomer. Okay, so this is what we have for today. So like today we discuss some of the basic concepts related to the various operations involved in the chemical industries like tray tower, pack tower, distillation columns. We have not discussed right now. We will discuss in the upcoming weeks for the same. So we have seen some of the agitated vessels, parched vessels, and some of the basic fundamental terms related to the tray and pack tower, or tower you can say, or plate tray or plate columns you can say. So we'll wind up today's sessions. Thank you so much for joining today's sessions. We will meet next week at the same time from 3 to 4 that on Saturday. Thank you guys for joining. If you have any problems related to the questions or some of the concepts related to the week 5, please let me know or drop a mail on the NPTEL 7 portal. You can also post in the forum mentioned in the NPTEL 7 portal for questions. We will be able to get back to you as soon as possible. Thank you guys for joining it today. Thank you so much.